This is an example that will show the heat transfer in an injection mold for making steering wheels. The mold is being cooled by the flow of water through two pipes, and we will make use of the new pipe flow module to simulate this. Not only restricted to heat transfer, the pipe flow module can also simulate mass transfer, fluid flow, acoustics, and the water hammer effect. In this example, I will define the physics and geometry of the model and then include the pipe flow network as embedded edges. I will then apply material properties and the domain and boundary conditions. The model will then be meshed and solved, and I will perform some post-processing. I will start by defining the physics for the simulation, where the pipe flow will be described by non-isothermal flow, heat transfer through the mold by conduction, and the simulation will be time dependent. The geometry of the steering wheel was originally a CAD file, which can be directly imported, while I have previously created the geometry sequence for building the cooling pipe network, which I then specify as edges and name it. The injection mold will use water as the cooling fluid. Water's material properties can be loaded from the material browser, which takes into consideration density, for example, as being a function of temperature. The mold is made of steel, while I have chosen to define the material properties for the steering wheel to be made from polyurethane. The pipe flow module includes a number of inbuilt parameters for defining a pipe's characteristics, such as the shape, friction models, and representative surface roughnesses. I can easily set the boundary conditions, including an internal one, for the heat transfer between the pipes and the mold. This includes a film resistance between the flow and the steel of the mold. The pipe network, mold, and steering wheel all have their own mesh types and sizes. As I am interested in how the mold cools over a period of time, I define the time range for which to solve the model. The solving process takes about 15 minutes on a 12-core processor. With the model solved, I can now use a number of the different post-processing tools in Kامسول multiphysics to present the results in an informative way. The visualization tools are augmented by other post-processing functionality, such as easily calculating the average temperature in the steering wheel over time.